So today we're going to look at eigenvalues, eigenvectors, and of course the reason why we do all this, which is diagonalization. And there was a question regarding problem 2 of today's homework, and this is precisely identical to the examples that we did last time, and it's exactly identical to the quiz that we just took. So you need to form the two matrices. So it will be 1 to -1, 0. So please do not attempt the homework without redoing everything that we have done. And then you put V on the left, U on the right, and you transform it to 1, 0, 0, 1, and whatever comes out. This will be the transition matrix. Okay, so very, very standard. Are there any more questions on the homework or on previous material, please? Okay, so last time we said that two matrices A and B are called similar if one is a matrix that is obtained from the other by multiplying on the left by a matrix and on the right by its inverse, or vice versa. I mean, you know, the inverse of P to the -1 is P. So you can say it either way. And we said that for all intents and purposes, matrices that are similar should be sort of identified. Why? Because they can represent the same linear transformation, the same linear map. So if we work on the basis of linear maps, then two similar matrices are just two different ways to visualize the same object. That's why it makes sense to say that similar matrices are essentially identical identical objects. Of course, in the sense that we just explained, they don't consist of the same numbers. So in a sort of naive way, you could look at them and think of them as being not necessarily the same, but as I said, for all intents and purposes, they are the same. And one quick thing before actually I turn to diagonalization, which is our main theme for today. I created a score for you on Blackboard, which pretty much sums up all the work that has done so far in the context of the work that you need to do to complete for this course. So don't be alarmed by the fact that what you see is kind of low, because it's the score that really tells you what grade you would have had the course ended right now, or if you decided not to submit any more coursework from this point forward. Of course, hopefully none of this is true. The maximum that anybody has had so far is around 47. Look, what you have is a percentage. It will never go down. But for the moment being, if you want to understand it in terms of absolute terms, you should divide by 47. So let's say if you have a 30, you divide 30 by 47 and you find your real percentage so far. Okay, as the scores keep coming in, this will become out of 65 right before the final exam. And the final exam counts for 35%, so that is going to pretty much be added. I have also subtracted the lowest scores, but at this point, it doesn't really give you any, it doesn't make any difference because the lowest score is already something for, is a 0 for the homework assignments and quizzes that you have not taken yet. So it's not going to give you any relief. If anybody has questions on their specific score or the meaning of the score altogether, please see me during my office hours. Okay, now I would like to close this parenthesis and go back to what I was just saying before. So one of the central questions that we asked last time, and we should expect to be able to answer it, is a given matrix similar to a diagonal matrix? We already said last time that the answer is no. So there are certainly even 2x2 matrices that are not similar to diagonal matrices. But today we're going to understand this question more precisely, and we're going to try to answer it when, or try to establish that diagonalization when that is possible. And the idea behind it is actually quite straightforward. So imagine that somebody gives you a matrix, and then by multiplying on the left and on the right by a matrix and its inverse, you get a diagonal matrix. So let's say that, and let me be quite specific. Okay, so the question is, how can you find that diagonal matrix? And what people understood from the beginning is that the numbers that you see on the diagonal are very, very important. Meaning, one might ask, is it possible for me to diagonalize a matrix and get 1, 2, and for somebody else to take the same matrix, also diagonalize it, and get 2 and 3 on the diagonal? And the answer is no. The numbers on the diagonal are numbers that are specific to the matrix. They're so important that actually we give them a name that is going to become a little more general very soon. But we call them, specific or special values. We don't say specific or special. We use the German term, which is Eigenvalues. So we call them Eigenvalue. And they're specific to the matrix. So the best or the most different thing you can get is, if you diagonalize the same matrix, is get those eigenvalues in a different order. So if you tell me that somebody else diagonalized the hypothetical matrix that I have written down, I can tell you for sure that they're going to get 2 possible things, either 1, 2 or 2, 1. Okay, one of the 2. They're not going to get anything else. Okay, they're not going to see 1, 3 or something else. Okay, so that's the first thing to understand. Secondly, what you need to understand is that this matrix works very, very nicely for vectors that are for the vectors of the standard basis. So if you take this matrix and you multiply it, let's say, by the this vector, which belongs to the standard basis, you will get exactly 0, 2, which is twice this vector. So for this reason, this particular vector is going to be called an eigenvector corresponding to the eigenvalue two. And now the situation, hopefully, will be clarified once we understand that eigenvectors and eigenvalues can be attached to linear maps, not just matrices. Sorry, you're absolutely right. This should have been one. Yeah, sorry about this. So, and now we can give our formal definition. So, lambda will be an eigenvalue of the linear map T if there exists a non-zero vector u such that T of u is equal to lambda u. So we're talking about vectors whose images are multiples of the original vectors themselves. The vector u will be called an eigenvector corresponding to lambda. We could give the same definitions at the level of matrices. So we could say, so for matrices, after all, remember, there is a dictionary that allows us to identify matrices with linear maps, right? So for matrices, lambda is an eigenvalue. And we're talking about square matrices here of the square matrix A if there exists a non-zero column matrix U such that AU is equal to lambda U. Then the column matrix U is called an eigenvector. So basically, when you have a matrix which is diagonal, all the vectors of the standard basis are eigenvectors for that matrix. And pretty much a matrix can be diagonalized if and only if. And when I say diagonalized, I mean it's similar to a diagonal matrix. If and only if there is a basis for the space of column vectors that consists of eigenvectors. Then in this case, we say that, we have an easy criterion for, I should say a straightforward criterion. It's going to take a little more effort to translate this to something that becomes more tangible. The space of column, of column vector. Okay. So okay. So what's the game plan here? Our game plan is to find the eigenvalues. So you will see that first we find the eigenvalues. And then we find eigenvectors. Corresponding to the eigenvalues. Okay, so how do we find the eigenvalues? Actually, that's kind of fun because look, we said that an eigenvalue is defined by the fact that you can find the non-zero column vector so that AU is equal to lambda U, right? So that would mean that AU minus lambda U is equal to the zero column vector, which is the same thing as saying that U minus lambda times the identity matrix times U is equal to the zero vector, which is the same thing as saying that A minus lambda times the identity matrix times U is equal to the zero vector. That tells you right away that this matrix, so I should say here there exists U such that this is true. And this is true if and only if the matrix is non-invertible. And when is the matrix non-invertible? When its determinant is equal to zero. So we do the following thing. The eigenvalues are the roots of the polynomial. I'm going to just change it just a little. I'm going to make it determinant of xi, the identity matrix minus A, which is called the characteristic polynomial. For a given eigenvalue lambda, this is the symbol for if and only if. This is the mathematical symbol that means if and only if. Okay. And for a given eigenvalue lambda, the eigenvectors are solutions are the non-zero vectors of the null space. So this is where null spaces come in. A minus lambda times the identity. So there are two things that we do here. First, we find the characteristic polynomial and its roots. So these are the eigenvalues. And secondly, we for each eigenvalue, we find the null space of this matrix. And if we have enough eigenvectors, then we can build a basis consisting of such eigenvectors. And that gives us precisely what we want. So the question that we're going to ask ourselves here is, what is a situation where this is guaranteed? And it turns out that if an n by n matrix has n distinct eigenvalues, then it is diagonalizable. So we can diagonalize it. And you know, the other really cool thing is that if A is a triangular matrix, then the diagonal entries are the eigenvalues. Okay. So, so in other words, for example, the matrix times ID, which where ID is the identity matrix. Yes, that's right. For example, the matrix 1, 2, 3, 2, negative 1, 7, 0, 0, 0, like this. This matrix is diagonalizable. Why? I can see what the eigenvalues are. The eigenvalues are the diagonal entries because this matrix is triangular. And they're all different. There are three numbers that are distinct. And for that reason, it is diagonalizable. Okay. So what is important is to do a detailed example where we show how this method works step by step. Okay, so let's do it for a 2 by 2 matrix so that we understand very well what is involved here. So diagonalize. So here's the example. Diagonalize the matrix 1, 3, 3, 1. Okay, so I'm giving you this matrix. Later on, when we do more theory, we will realize that with eyes closed that this matrix is diagonalizable. Okay, but for the moment being, it's a good question of why this matrix is diagonalizable. You're going to see that it is, though. Okay, so let's see how we do this. So the first step always is to find the characteristic polynomial. What is the characteristic polynomial? The characteristic polynomial is going to be the determinant of the identity matrix minus R matrix. Okay, so oops. So in other words, let me make this as clear as possible. If you get the identity matrix, you multiply it by I, and from this you subtract our matrix, then you get a matrix whose determinant you should take. Okay, so you should take the determinant of this matrix right here. Okay. So how much is this? This is x minus 1 squared minus 3 squared, which by the identity of difference of squares, this is x minus 1 minus 3 times x minus 1 plus 3, which is the same thing as x minus 4 times x plus 2, right? And if you set the characteristic polynomial equal to 0, then you will get x is equal to 4 or 2. So the eigenvalues are 4 and 2. So we're expecting our matrix to be or rather, I could write it this way. So we expect our matrix to be similar to the matrix 4, 2, 0. And, you know, of course, here there is the obvious question. What would happen if somebody decided that I don't want 4, 2, I want 2, 4? That's perfectly fine. Nobody tells you in what order you need to select those entries. That's sort of irrelevant. Okay, now the main question here, if you want to realize your diagonalization, is to find. So the big question here is, how do we find this matrix P? Okay, so the moment you have the eigenvalues, if the eigenvalues are distinct, and I think in this course mainly I'm going to ask you to work with matrices that have the right amount of distinct eigenvalues. That is, you're going to have such a really nice case like the one you see here. The question, once you find the eigenvalues, is how do you find the matrix that transitions you from your matrix to the corresponding diagonal matrix? So that is going to be the question. Are there any questions so far? So we need to still find that matrix P. That we're going to give it a name. We're going to call this matrix P the diagonalizing matrix. So this is going to be called the diagonalizing matrix. Okay. Oops, -2. You're absolutely right. Ooh, sorry. Thank you. It's -2 at both places. So I need to change it at both places. Thank you. Okay. So what do we do? We're going to work with each eigenvalue separately. So for let's start with x equals 4. The key is to rewrite this matrix. So rewrite this matrix for x equals 4. What do you get? You get 3, negative 3, negative 3, and 3. And you want to find the null space. How do we find the null space? Remember, that was the last question on the previous exam. You get the augmented matrix with a 0 column, right? So now, and you need to apply Gauss elimination method. So you're going to do 1/3 row 1. And this is going to give you 1, negative 1, 0, negative 3, 3. And now you're going to get minus or plus 3, actually. Plus 3 row 1 plus row 2. So this is going to give you 1, negative 1, 0, 0, 0, 0. And please don't be alarmed. In any, whenever you find eigenvectors, you need to find the 0 row. You need to find the 0 row. Okay, that will always happen. So then now you go back to your system. And the system, see now I have used X, right? That's why I will turn to lambda next time. But for the moment being, let's say that we have X minus Y is equal to 0. And then there is an equation consisting entirely of zeros. We don't worry about that. The bottom line is that the column of the Y's is going to correspond to a free unknown, right? So X is equal to Y. So your eigenspace, meaning the space of all eigenvectors. So eigenspace, that's a new nice word. Eigenspace is space of all eigenvectors. So again, I got this matrix by substituting X equals 4 on my matrix that I used in order to find the eigenvalues. Okay, if you put X equals 4, you will find exactly the matrix that I got. So this will give you Y, 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 and Y. And of course, you need just one eigenvector. So Y, 1, 1. So I will take it to be 1, 1. So that's my first eigenvector. Okay. That's my first eigenvector. Could you please go ahead and do the same thing? So repeat the process for X equals negative 2. So please do the same thing for X equals negative 2. And you should find another eigenvector, which is linearly independent to this one. The good news, the great news, is that eigenvectors that are correspond to the same eigenvalue are always linearly independent. That's great news. I mean, it really clears things up for us. Okay, so please do the same thing for X equals negative 2. Okay, I'll give you a couple of minutes and then we'll do it together. Okay, so let's see. So if X is equal to negative 2, then what is the matrix? Do I remember it now? It was, I believe it was negative 3, negative 3, 0, negative 3, negative 3, 0, right? That's what it was. And I do a negative 1/3 row 1. That gives me 1, 1, 0, negative 3, negative 3, 0. And then I do a 3 row 1 plus row 2. So again, for the first step, as we said a moment ago, we go to our matrix whose determinant gave us the eigenvalues, and we plug in the eigenvalue, which was -2, right? And we find this matrix, and now we're going to find the null space. So once you do your elimination, it's no surprise that you will find 0, 0, 0. And so you end up with the equation x plus y is equal to 0. This will be free, and x is equal to -y. So what you get is minus y comma y, which is the same thing as y times -1, 1. Okay, so this is the second eigenvector. So what do we do now? We take the transition matrix that has the eigenvector. The first eigenvector that I had was 1, 1, and the second one is -1, 1. So this is the diagonalizing matrix. And to finish the whole thing, we need to find also its inverse. So we need to find its inverse. So what is the inverse of this? Using the formula that we have seen directly, this is going to be 1/2 times 1 and 1 here. And then we're supposed to put 1 and -1 here, right? Which gives you 1/2, 1/2, -1/2, and 1/2. So now we want to produce the diagonalizing equation. So the diagonalizing equation. Which is going to be that the original matrix that we had, which was what 1, 1, 3, 3. On the right, we multiply by the matrix, the transition matrix. On the left, we multiply by the inverse. And what we're going to get is the diagonal matrix, and the eigenvalues appear in the order that we put them, like this. So had we worked first with -2, then with 4, of course, the entries would have appeared the other way around. So this is the matrix A, this is P, this is P to the -1, and this is the diagonal matrix. And this is the kind of work that we need to do in order to diagonalize a matrix. Now, the natural question to ask here is what happens if the matrix is not diagonalizable? Where will this whole process get stuck? It will get stuck to the fact that you're not going to get enough eigenvectors to form a whole matrix. So let's say if you have a 2x2 matrix and all you can find is one eigenvector, that's simply not enough. Okay, or if you have a 3x3 matrix and you find 2 vectors, then this is still not enough. And you will see, I have a very interesting problem for you. That's problem number 3, where a matrix for which you cannot find enough eigenvectors is dubbed a defective matrix, a defective matrix. Yeah. Now, generically speaking, you could ask, is every matrix diagonalizable? So in the same way that every matrix is generically invertible, not every matrix is invertible, but the probability of finding an invertible matrix is a non-invertible matrix is pretty much 0 if you do it randomly. So how about diagonalizable matrices? Here the answer is no, it's not true that it's 0, that generically every matrix is diagonalizable. And one of the reasons why you have this situation is because, as we're going to see, eigenvalues do not have to be real numbers. So if you were working over complex numbers, then the answer would have been yes. Generically, every matrix is diagonalizable, because for it not to be diagonalizable, you need to have the same eigenvalue occurring more than once. And even if that is correct, then still there are other things that have to go wrong. But other than that, all other matrices are diagonalizable, but within the real numbers, and that already gives you an idea of why people prefer to work with complex numbers rather than real numbers. Anyhow, let's leave it at that. I want you to think of any questions that you may have, and when we come back, we're going to do one more example. Let's actually do a 3x3 example when we come back. Okay. All right. So let's take our break now.